Hello, welcome back to your physics teacher with me, Mr. Fernando. In this video, I'm going to be showing you how we can determine the direction of the velocity vectors from displacement vectors. So, the story so far, here we have our friendly cheetah and we have the tree. And let's suppose that our cheetah, which we can represent by a particle model, we place it at the center of its mass, and this is where it first begins. So, where we begin our timer at t0. And the cheetah moves along to the right. After 1 second, it continues moving to the right, and then maybe at the 2-second point is down further away. But in order to draw velocity vectors, we need to know displacement vectors. Now, why is that true? If you quickly recall to our position time graphs, what was the slope of the position time graph? Well, the slope of the position time graph is going to be the rise, which is the y values, but in this case the d, over the change in the x values, which in this case is the time, which is the change in d values over the change in time values. So another way of thinking about it is just going to be our displacement over the change in time. But that's in our graphical representation. But all along we were dealing with vector quantities because this was indicating the direction east. So it had a magnitude and direction, which was a vector all along. So this should also be a vector. And it turns out that the slope of the position time graph is actually just our average velocity, or in some cases it could actually be the instantaneous velocity, but to be lazy we can just call it velocity. Delta d over delta t. That means that in order to determine the direction of velocity in a motion diagram, we need to figure out the direction of displacement. Why is that? Well, we can really think of this equation here as delta d times 1 over the change in time. Now, the change in time is always going to be a positive number, right? Because if you start your timer at 0, and the next measurement is at 1 second, what's the change in time? 1 second. And after 2 seconds, what's the change in time? Another 1 second. So this is always going to be a positive number. So greater than 0. That means that we can determine our velocity vectors because they are going to be in the same direction as that displacement vector. They will be in the opposite direction if this was a negative number, but since it's always a positive number, these two are always going to be parallel and in the same direction. But it turns out that we can do a better approximation if we keep our time interval to be nice and innocent. And what I mean by that is to keep our time interval to be 1 second. So if we assume this equation becomes a lot easier. That means velocity equals to our displacement vector divided by 1 second. But technically you could like disregard this for now. And what does that look like? Our velocity vector is the same thing as our displacement vector. So our mission now is to figure out, A, how do we draw displacement vectors, because that's going to give us the same direction, and, if we assume 1 second, the same length. Right, so if we assume that 1 second of time interval, the direction of velocity is the same as the displacement, and even better, they're going to have the exact same length. But keep in mind, as a caution, they are different quantities. Right? Because our displacement is in units of meters and our velocity is in units of meters per second. So they're going to look the same, but they represent different quantities. So what's one way that we can do the trick? Well, even here's a hint. We can use one color for one quantity and we can use a different color for a different quantity. So now that this all comes down to just A, to determine the direction of velocity and length, all we need to figure out is the displacement vector. So if you recall in a previous video, displacement vector is the change in position. So if we're looking at 0th frame to the first frame, the change in position was this length between the two in the direction towards the evolving time, so towards time 1. So we have our first displacement vector, delta d0. And for the next time interval, we just connect the dots again. And our second displacement, so we call it delta d1. Very easy. So now, in order to draw our velocity vector, since they are the same length, same direction, we can just draw them below one another. But because it's a different quantity, we use a different color. So this represents our initial velocity, v0. And the second part represents our velocity 1. So let's write this down quickly. Because this is the most useful quantity for the remainder of the course, more or less. V initial, sometimes it's written as Vi. This represents the initial velocity. And V1 is the velocity at time t1. Alright, so what is the main conclusion? The main conclusion is whenever you're drawing a motion diagram, our velocity vectors can be drawn in the same direction as the displacement vector, and assuming there's a 1 second time interval, they are going to be the same length. But remember, try to use a different color, so that way you remember that there are two different quantities that we're talking about. Now, hopefully you got this main idea. In the next video, I'm going to be showing you the different types of motion and what the velocity vectors would look like, and later we will do an acceleration.